Screen share. Okay.
I didn't realize how unusually slow stuff. Okay, these are your broadcasting.
So today we're doing satisfiability for stat and graph coloring. So in the domain direction, we will find an assignment of truth values such that the entire expression evaluates true. And we'll take a look at them later. When an expression doesn't have any arguments that make it variable, that makes all the variables true, it's said to be unsatisfiable. I'm going to be true for the next hour. And then there's the satisfiability decision problem, which is whether or not the truth value, an assignment of truth values actually exists, and not necessarily what it is. So there's sort of two separate problems. One is to find a set of values. The other one is whether or not a set of values actually exists. So we generally get these in the project sums format, which is just where you got these are all, we remember from B, these are all of our fours, so that's X1 or X2 or X4, and if with that, not bars are off. Okay. Sorry about that. And so to solve this, we can generate all possible assignments systematically and test each one to see if it satisfies the expression. And this is exponential 2 to the n, where n is the number of variables in the expression that we have. So we can look at the truth table and fill out all of our values systematically going through and see which ones actually fulfill our expression. We can also think of them as a circuit. And so we can go through our circuit and see which ones cause it to be true. So this is lectures, and I don't know if anybody else has played with this or not. It's kind of fun. So we can, so 0, 0, 0, 0. Sets this line of expression true. This is the same one on the previous slide, which I lost. Where did you go? Yes. Yeah. So when we change up these input bits, we see that 1, 0, 0, 0 is not a true assignment that causes this to be true. The little LED went black. Also, our output pin has a 0 on it. So if we wanted to, we could go through and test these systematically, checking each one of their 1, 1, 0. But that takes way too long. It's exponential time, and we don't have that. There is a somewhat faster way, not for all cases, but for most of them. It's the database algorithm, and what it does, it recursively creates a search tree for each expression and makes partial truth assignments for that expression. It's able to prune unsuccessful branches from the search tree, and it can, if the expression is not satisfiable, it will generate everything, so it will get exponential time. But if we're just wondering if there is a truth assignment or if it exists and the expression is satisfiable, we're likely to find it faster than exponential time. Or doing exhaustive search. So the way this algorithm works is you have an expression. So our expression is E. We split it into pieces. If it is an empty clause, we return. If there are no clauses, so those are our base cases. Empty clause return or third clauses, then we add with the partial assignment. We still index an assigned variable in the expression, and we split it on that with it 0 to equal to 1. And it makes more sense to go through see if that's actually visible. Kind of.
Actually, I think that's
Video.
yeah, I think so. No, it's not fantastic.
Okay.
Maybe if you make it bigger.
I can write bigger.
Yeah. Just losing.
Really a lot of space.
Just lost video.
Lost video.
I mean, like possibly. I'm not sure that's what it was. It could just be too much for this little thing.
Oh, yeah. So, no,
Yeah, see.
on.
No! The camera.
We're recording for him.
Okay, it's back.
It's back.
No, it came back.
Alright.
I'll watch this. I swear I didn't do anything for it.
Oh, I lost some slides. Oh, well. I'm using them right now anyway. Okay. So the first variable we're going to split this on is x1. So we're going to have equal 0 and equal to 1. And so then when our x1 is equal to 0, we go through our full expression, and clauses that have not x1 in them are going to be totally removed, and then we're going to remove from the other clause itself. And we're going to do the opposite on the other side. So this is going to just become x3 naught or x4, and with we can get rid of that entire clause, and then x2 naught, x3, and then also get to remove that entire clause. So then on this side, we are going to remove any clause with x1, and we're going to remove any instance of not x1 from the other clauses that exist. So this is going to be x2 or x4 not, x2 not, x3, and x2, x4. And so then we're going to split it again. And the next variable that we have is going to be x2 if we just go in numerical order.
Would you possibly not? Because you can look at else, there might be a better choice.
I mean, if you do that, x3 would be a better choice than you got here, but we don't.
No, I'm just
But yeah, I mean, if you had some way of knowing that, hey, we want to get rid of this variable, like, you might be able to do a count before you run the algorithm and be like, well, there are like 7 instances of x1, so we should figure it out first, and there are like 4 of x2, but there are 5 of x3, so there probably is. side, you're not that X2 clause out, so we just did. Yeah, we just end up with X4. And on this one, it's going to be X4, not X. And drop out the X2. So our first time is going to be 0, 0, 0, and then either 1 or 0 for X4. So anytime we get a clause that falls out entirely, there's nothing else left. Anything below it is going to automatically. They don't care. Then for this one, though, we are going to end up with X4. So we'll have to expand that further. But we don't have to expand that way anymore. For X3, you can see over here, we're going to end up with this becoming an empty clause. And so there aren't going to be any further assignments. And this is the notation they used in the book, which took me a while to get used to. Going through it was it's got the parentheses that clause is empty. It wasn't just like thrown away like that one. So that means there's nothing further down this tree. So we don't have to evaluate anything.
So in that first mod, it's going to be true, and it's going to be false. And that's going to be false.
Yeah, anything further down this branch of the tree is going to evaluate false. We don't need to go any further. And so then this one that we're just going to end up with. So X3 is going to be X4. This one, again, we get the empty clause. So anything further is going to evaluate to false. And then this is going to be X4. And so then our last go through, maybe X4, 0, 1. We don't have to go any further down this branch. 0, X4, 1. Don't do that one. Okay. So then when XOR is equal to 0, this will evaluate to false. So this doesn't have any, but this does. When XOR is 0, this is false. So that won't have any assignment that works. This one will. Same thing here. And here. And then opposite here. So that is counting. So 7. There's 7. And if we go back and look at our truth table, it's the same 7. If we want to write them down, all we would have to do is to follow first the tree. Yeah, basically traverse the tree. And then here we have the 0 or the 1. So anything that the branch is labeled with is our table. So it does, like, we did it especially here because we got all of them. But if we were just wondering if there was a sign, we just stopped right when we got to here.
Started out for a second.
So that, if we were just wondering, is this problem satisfiable, it would have been far fewer steps. They didn't give in the book like a best case, but I think it would be log. Yeah, your best case would be to know the first try where all of your variables evaluate to 0 to be true.
Best case would be you have determined each of the satisfiable settings. So you can just get one.
Yes. In all of the individual systems. Yes. So yeah, they didn't give.
If you have not X1, yeah, they're all just X1 or not X1. Right. Okay, let's see.
John has joined us.
Okay. Hi, John.
John, can you see the board or could you?
I can somewhat see the board, but the audio quality is really poor.
Yeah, we have a little EE PC here that's not very good. I think this cannot handle it. You want to turn on your mic?
We can try. Okay, is that audio any better, John?
That sounds way better. The other one was...
Can you hear me at all?
Yeah, I can hear you.
Oh, we can't, because...
Oh.
Now, okay, now I have sound. Can you hear us?
Yeah, I can hear you.
Okay.
Technology. Is that any better?
Yeah, I can hear you very well.
Okay.
Everything is clear.
All right, we'll use my computer
Thank
audio
you.
then. All right. Okay, so back to the slides. So that was our search tree example. If we wanted to go back and look at our truth table, we do indeed have 7 expressions that evaluate to true. So that's kind of cool. Yay, we did it right. And I will get the slides and the Logisim circuit up on the drive at some point this afternoon. So this is important because we can use SAT to solve graph 3 colorability. We can make that transformation. And we'll get into why that's important a little bit later on. But given a graph with vertices V and edges E and the colors red, yellow, and blue, for each vertex in the graph, we're going to output R or Y or B. And then for each edge, we're going to output not R, I, or RJ. That it's easier for you to read than for me to try to talk that one out. And then we're going to assign values as follows. If it's 1 if it's red, 0 otherwise, for that particular vertex. And so if we look at it, every vertex will receive 1 color. So one of the variables in RI or YI or VI is going to be true. So that's this one right here, where the mouse is. It's in the mouse. So every vertex will get 1 color, so that will evaluate to true. And then wherever they are joined by an edge, they should receive different colors. And they cannot both be red, so either one of these has to evaluate to true. So one of these is 3-colorable, one of them is not. If we want to, we can go through and write down the Davis-Putnam algorithm for them, but we don't have the time or the space to actually solve it because we're looking at 7 vertices, and if we were to traverse the tree, we would end up with 49 if we were to go all the way down and work it out. So this is left as a exercise for the reader in the book to go through and solve this one. If we want to, I was thinking we could do a slightly easier example to do the transformation. What's that?
We have 3 nodes.
Yes. Well, in the example I was thinking we could do would be for 3 nodes because it's still really big. But before we get into that, this is important, an important transformation because we can use it to prove that 3-colorability is NP complete. So we have to prove that the problem is an NP. That's going to take polynomial time or non-polynomial time to solve. The graph colorability, I'm not. Okay. Yes, but my section is not on proving NP completeness, so I didn't.
One's just
If you just want
Okay.
to do it for me.
Yeah, I didn't want to do your work for you, but we can output that transformation in polynomial time, and the graph is 3-colorable if and only if our expression for the graph is satisfiable. So we'll do the 3-node graph. Good marker. So over here. Okay, so the first thing we're going to do is our vertices. So we've got. Sorry? Oh, okay. Or Y1 or B1. And then for vertex 2, we have R2, Y2, B2. And for 3, R3, Y3, B3. And then for each edge, we're going to have edge 1, 2 is going to be from 1 to 3 will be and then our last is going to be from 2 to 3. Okay, so that's what we have to split. What do we want to split it on?
Like our choice matters.
No. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
All the variables used in the same number of places.
Yeah.
So they don't think the first split matters.
No, but I'm trying to. We have 5, 6, 7, 8. We have 12 different variables.
Well, 9.
Isn't it?
9 variables, 12
1, 2, 3,
clauses.
4.
We just so yeah.
Oh yeah. So if we were to work out this entire tree, we'd end up with 81 if we needed every tree assignment. So we can just sort of, well, let's split it
We
on.
could do a depth first search kind of thing.
Well, aren't we almost positive we're not going to have to go down all the way to the bottom?
We
Yeah,
should.
well, if you if you do a sort of, you do a DFS, you did a BFS before.
Right.
But if you do DFS,
DFS,
then
we
you
could
probably go a lot
get
quicker
really
if you just want to find one.
Yeah. Okay. So we'll do R1.
Just produce the set.
What's that?
Sign whatever. All right, go ahead.
Okay.
Go ahead.
Please.
I'm going to use a different color so we know. Okay, so we'll start with R1. And we're going to end up getting rid of...
Which one is stronger?
One clause goes away.
Yeah. So then we're going to
A
have...
whole bunch of shrunk.
Oh,
Actually,
Still gonna be nice.
it's still
two of
going
them
to
are
be...
shrunk.
Yeah, this is going to shrink.
It's not gonna go away.
No, this is going to go away. That's going to shrink. That's going to shrink.
Maybe I misunderstand.
And then if R...
Yeah.
R1 is equal to 1,
Forward.
we're just going to end up with that.
Go away.
And that's going to go away. And that's going to go away. And the next one will go with Y1.
Is that not backwards?
What?
No, I think she's right.
I'm pretty sure.
Is that not? Because the ones that shrunk should have gone away because they're satisfied. It's
Yeah.
surpluses, right?
Well, it depends on which value you've already picked.
Yeah, for
I guess. So if R is 0, R1 is 0.
R1 is
you're
0.
right, the second term should just go away because it's satisfied. Right? Am I crazy about that?
I think you flip the colors.
Did I flip the colors?
That's why you put a line through it. Or no.
I flipped the colors.
The purple one should
Because
go
if
for
it's,
R1
if
equals
it's
0.
0,
Oh, we got it
Yeah.
backwards.
Yeah, okay.
I have that.
Okay.
good
Gotcha.
job, Dan.
Oh my god. I was
I wasn't. I just accepted it. I just
Okay, so then
Where's
for...
the-
Oh, this is...
It's really not going to matter which one you pick.
Right.
using our Oracle knowledge, we're gonna have to give each one a different color. So, I mean, R1's good. We could have R1 be
Let's do
true and
that.
the other R1's be false. And then,
And, you know, that... I mean, it doesn't...
Three.
Yeah,
crossed away, but yeah.
those are different colors.
Okay, yeah, I don't know.
Okay, so then for R1, we've got...
Wouldn't one of the quickest solutions be to look at like Y2?
They're all
I think you've got to assign the truth values no matter what. So you got to go.
Yeah.
No, but if we do all the ones,
Hang on. What? I'm not sure what you're doing here. Are you actually doing a DF? I mean, you would pick a value for R1, right?
In which case we wouldn't
Yeah.
look at.
So we were
R1
not gonna look
zero.
at
You
the
would
other
look at both
R0s.
possible. You'd pick one of them.
All right.
Okay, and that means the first clause goes away,
Yes.
and those other two shrink,
No.
and then
Okay.
Let's set
Let's-
the other. Let's set Y1 and B1 equal to 0.
Let's choose one. Completely
Alright.
arbitrary, right? Air quotes
Let's
arbitrary.
make our DFS choice.
well, I mean, if you tried Y1 equal to 1,
then you should
First,
set
you should,
the other
yeah,
ones
you
to 0.
then you should.
I guess we can try. Yeah, let's try Y1 equal to 1.
Huh,
Erase the B1.
wait, hang on. What happens?
Third clause goes away.
I mean, I know there is no solution with R1 equal to 1 and Y1 equal to 1.
So what should happen is it should collapse onto a.
But I think eventually we have to assign. I think it's going to be a conflict at the edges, so it's only going to happen once we assign.
Oh, hang on.
Y3
Isn't there something missing here? Don't we have to say not merely? I mean, your first clause there says that vertex 1 gets at least one color.
Mhm.
Don't we want to show that it gets exactly one color?
Oh, it can only be colored.
In other words, that we can't have both R1 and Y1.
I thought that's what the edges did.
No.
No,
just
no.
Is that-
No, because
Yeah,
that's
the
just
same.
for sat. That's just for satisfiability. This is for graph coloring, which is slightly different.
But it is if
So you're actually allowing a vertex
So-
with multiple
Yeah.
colors here.
Right.
But I guess that would be good enough because then you just pick one of them.
Pick one.
Your conditions say that the sets of colors on adjacent vertices do not intersect.
Right. So we would have to get rid of.
Right?
Well, I mean,
See,
it'll
well,
R1 and
yes.
Y1 could. I don't think there's any solution with them both true, but they could conceivably
And
both be true. I don't think this particular.
that won't produce erroneous yes.
no.
Okay.
Yeah, because that's like choosing
Suppose you
it.
had
It could be
something
yes,
like
it's
this.
just a path.
Okay, you
One
could
could be two colors because the other one was just chosen.
you could color them like that.
Right.
Okay.
And yeah, and
With-
either of
that's
those would
vertex 0, Y0, and B0 could
are
both be true.
Yeah.
Now that isn't any color for that particular graph that works, but that's really what this system,
Yeah.
this Boolean
Transformation.
expression is saying.
Polynomial transformation.
Okay. So should we do y2 equals 1?
We already just said. Sure. Well, we should probably actually not go down a path we know is not going to be true.
Y2
How can
equals
y2
fine.
not be?
Oh, Y2 equals 1.
Y2.
would work. Yeah.
Y2.
Yeah.
Yeah.
That's interesting.
Yeah. So then we get to get rid of that. That. And then
E3 equals.
E3 equals 1.
Doesn't know white.
That. And E3 is 1. To get rid of
And the far right on the top shows.
there. All right.
And now it's
The only thing you pick, I mean, if you say R2 equals true, your second clause is going to be empty. Then you're going to backtrack. And so you're going to try R2 equals false. If you try R3 equals 2, then you're going to backtrack off that 1, 2, 3, 4, the fifth clause. And so R3 is false.
Is it just the
I
main
think
one?
that's going to give you all the
It's
rest.
just going to
false.
force you to set the remaining ones to false.
Yeah.
2, R3, B1, B2, and Y1, Y3.
Wait.
Yeah, you do get all of them that way.
That is what we will end up with.
That leaves you with no more clauses.
And that's for 3 nodes. So we really don't want to do that 7 node one.
This isn't that hard. That's why we have computers.
Right, exactly. This is why we should write a computer program to do this for us, which I did not have time to do before this class. And I think that is all I have.
We get started on the cook level.
I've looked at it. I'm not ready to present on it.
Okay. But yeah, these are the slide that you can't see is 2 of the 4 important bits of proving the NP completeness. I'm sorry, that's horrible.
The 4, the triangle at the top.
Yeah, but that's
I don't have
it's.
enough information.
But the idea is that you don't. I mean, it doesn't matter, right? It's okay that there's more than one truth assignment that satisfies,
Especially for the decision problems.
right? Because there actually is more than one coloring that will satisfy as well.
Same with just the 3. I mean, you could.
So it seems like it's a good concept for a problem. Yeah.
What question? Do you know, or does anybody know? I mean, there are top quality free set solvers out there. Is Davis Putnam what they use? I don't know. I don't know how they work.
Never had a need to.
I'm interested in implementing the algorithm.
They have to because okay.
Oh,
so
that's my. Where's
Like,
my
where does
stop?
Something else, right?
Quartz has to be able
There.
to do it because it just does stuff.
Wikipedia.
Yeah, actually.
DPLL. I'm assuming
Guys
Davis
with last
Putnam,
name L.
Lodgeman, Loveman.
Love.
Backtracking. Oh, so I guess they were.
Basis for
One of the most efficient complete set solvers.
use of extent for automated theorem for fragments of first order logic. So you just type in a proof that you want to prove. Oh man, that's how we solve it.
Okay. We want to see what the other ones were. Chaff.
Instance.
Enhancements for efficient implementation.
Oh, zchaff. Yeah, I've used zchaff. But no, chaff was the algorithm.
Okay.
So there is satcompetition.org, which is the International Sat Competitions webpage. And they have lots of different ones on here. Yeah.
People are really into sat, I guess.
Yeah.
It's a pretty big area of research. So. Grasp. Graphic search algorithm for the satisfiability. So he came up with a clever acronym.
It's,
Pull the R out of search there.
Well, the R is, search. There's not even really an R sound to it. Sats?
It's the last version of sat solvers. It's the one that end all sat solvers.
there will never be another. Seriously, I saw a program in like 1980 for sale. It was called The Last One. It's supposed to be the last program you ever buy because you just tell it what you want to write all your other programs for you. I thought it was a joke, but I saw somebody mention it. He apparently was serious.
Well, there's always those guys that are like, I've solved security.
I've solved everything.
Yeah. And actually, it was good, but we had him done away with because he would put us out of business.
Yeah. Science Illuminati.
It actually worked. They just, took him into the back room.
Solve the weighted satisfiability problem.
It's a weighted
I don't know what.
Click weighted satisfiability. I kind of want to see this now.
Max sat.
satisfiability. Oh, maximum.
Determine maximum of clauses.
So if you can't get a good one, it's the. Am I getting that?
Conflict-driven
It's many
clauses.
clauses
As possible, yeah.
Which for satisfiable.
So even if it's not satisfiable, maximize the number of clauses you can make true. Yeah.
Okay. That's interesting.
Conflict-driven clause learning. CDCL, but they're based on DPLLs. So I think they're just.
Seems like everything's like.
I think everything's gonna be based on it because it's a backtracking search.
It's a.
It's the most basic. You're gonna say it's based on it because it backtracks. Unless you do
You try to be really smart about when you backtrack.
Mm-hmm.
Or maybe even
Or
selecting
how
the
you.
order.
Do we know what NP hard
So
means?
there's parallel
Max
solvers,
set problems
which I
NP
think
hard.
might do something different.
We have not talked about that
Yeah.
yet. So.
Okay.
So NP hardness is.
NP hard is basically half of NP complete, roughly speaking. NP complete problem and NP hard problem, that's in NP. It's a little bit fancier than that because it allows things that are decision problems.
NP hard, isn't it? Or also
Basically, a problem is NP hard if you can solve satisfiability quickly by using it as a subroutine. It's a little bit more general than returning its return
Return.
value. But this max set problem, not a decision problem, so it can't be strictly speaking.
NP complete, because NP complete is all decision problems.
It's a cool fun.
Are you more to say?
No, we hit my last slide.
I have a relevant little story.
Okay. Yeah, well.
So this is, so Dr. Hartman and I, a bunch of others, were looking a couple of years ago at the question of representing a graph, representing a graph so that you have regions blocking edges that aren't there. So, I mean, that's a lousy drawing. This graph can be represented with one region, and that blocks those two edges, and all the other edges are unblocked. Make some sense?
What do you mean by blocking?
So the question.
John's asking what you mean by
What's
block.
that?
John is asking what do you mean by block.
Oh well, if you draw, you put the vertices in the plane, and you specify the region, and if you try to draw an edge between two vertices and it hits the region, then it's blocked. That's a straight line. Yeah, you can get there, but not in a straight line. It's called an obstacle representation. And then the question people ask is how many obstacles are required. And it's really difficult to find a graph that you know needs even 2 obstacles. Because there's all kinds of the edges, they don't have to be, let me do one. Here's a one obstacle representation of the 5 cycle. Okay. Those edges are all blocked.
Yeah.
In kind of a non-obvious way. Nobody, I believe until we did it, nobody had ever actually found. They knew there were graphs that required lots of obstacles, but nobody had ever actually found one that needed more than one. Okay. And we were able to find one using a SAT solver, which was a little bit of a surprise to me. So we had, yeah, I don't think I want to go into all the details, but we have 3 vertices here. The clauses in our SAT solver were all about this vertex is on this side of the line between those 2. So we had, not clauses, variables. So we had variable, that variable might stand for the statement that vertex 3 is on that side of that line. If that variable is false, it would mean that D3 is over here. Okay. And we were able to make those variables to turn them into a bunch of clauses that essentially expressed the statement that there is a path from one of those variables to the other on one side of the line, and then there's another path from one of those variables to the other on the other side of the line. So if there's an obstacle out here, it can't block that edge. Okay. And the resulting, we did this on a graph with 12 vertices and 30 edges, and the resulting number of clauses and variables was just enormous, you know. But SAT solvers could do it. So you know, maybe I don't remember exactly, but I'd work up the whole Boolean expression, send it over to the SAT solver, and then about an hour later, it would say, "Okay, I got an answer." And who knows how the SAT solver works, or if it's buggy. So we ran it on like 3 or 4 different SAT solvers, including the ZChat was one of them. And they all gave the same answer, and I wrote the code, and Hartman wrote the code separately, and we both ran it on set solvers, and everybody got the same answer, so we're pretty confident in it. So the graph we were able to prove is actually the icosahedron.
The camera on the EEPC has turned off?
Somebody's going to have to translate John for me. I can't.
He said that the camera was turned off. Is mine sharing at all?
You are sharing your desktop, but not the camera.
I will stop sharing my desktop because we're not.
Oh, the other one has turned on.
Drawing.
Well, there are two cameras. So.
Oh yeah. Right. I get it.
Okay.
Okay, so
Is that better?
The graph formed by the edge.
Yeah.
It was like a 20-sided die.
Okay.
Okay, so it's planar, and that's how you get it to draw it flat. And we're able to prove that does in fact require two obstacles. Again, using a SAT solver with hundreds of variables and clauses. So there's an interesting issue here. You know, this SAT is NP complete. We know no polynomial time algorithm to solve it. But we know algorithms that are fast for a lot of SAT instances that actually come up. I don't think anybody really knows why or has a handle on that. What is it fast? It's just for real practical problems, it's often fast. We know there are problems where it's really, really, really slow, but they just don't come up.
So what is?
So where are the regions? Yeah.
What are the obstacles you can draw on that?
Oh, yeah, we've got. I can send you a picture. The graph looks crazy. It's got a bunch of edges here, a bunch of edges here, and there's all these vertices, all these edges going around. There's this obstacle here, and there's this obstacle out there, and it's Leah Berman from the math department drew the pretty picture of it. And
Cool.
that solver did not find us a two-obstacle representation. It just proves that there wasn't a one-obstacle representation, but she found the two-obstacle representation and drew. Thanks to Leah Berman, my papers are pretty nowadays. She's very good at drawing that you could use. I'm not.
Are these vertices fixed in space, or can they be moved around?
John's asking if these vertices are fixed in space, or what was the rest of it, John?
Can they be moved around?
Or can
Because
they be moved around?
I would think
Yeah,
that
yeah,
if they can't be moved around, then you can.
All vertices here, and we want to be able to place them in the plane somehow, and have two blobs somehow
So you showed that
that block all the non-edges but not any of the edges.
So no matter how you embed that graph, it always requires two obstacles, is what you showed, right?
Oh, at least there are some embeddings that require a lot more. I mean, if you do it like, I don't know about that one, but it always requires at least two.
At least two. Okay.
It can be done with exactly two. And so I've never done anything. I don't know, 2-3 years ago. I've never done anything like that before or since. Used a SAT solver to prove a new mathematical result. It worked.
That's pretty cool. I don't know. He's like, yeah, I'm just gonna start slamming random things into the stat solver, see what I get. Go find something that reduces to that stat instant.
Okay.
Cool.
So I can't say how common that is. I've never run across much work done with SAT solvers. I mean, using them, but people write them. You know, so there are a dozen halfway decent ones out there. People must write them for some reason. But I'm not really sure what people do with them in practice.
It sounds like the current research in that is saying, so it sounds the current research in SAT solvers has been optimizing DPLL, but the current idea is that to get better than where they are now, they're going to have to find non-DPLL solutions. And there's a few, but they're not good enough yet. But I cannot find examples of those few.
I think the last set solver I've ever would probably.
Do it.
I would have to, wouldn't it? I've never heard of it. I don't know.
Have they proved the four-color theorem?
What's that?
Have they proved the four-color theorem? I know they used a computer.
Yes, they have.
Yeah, but did they use SAT to do it? The SAT solver?
Not solved. No, I believe all the proofs have been using a computer, but the ones they did, there was more or less a proof back in 77.
Yeah.
Which the general technique is held up, but they did find some errors in it. But they did one in the year 93 using the same, more or less the same technique, but they had the web and people could share the code and find bugs in it and run it on their own machines and all that. But since then, a couple others have been published. So yeah, it's pretty well established as true these days.
But it's not the SAT solver. It's not a SAT solver.
The first two proofs didn't use SAT solvers.
Okay.
I don't. Maybe some of the others have. I wouldn't know.
I was just curious. Probably somebody's not playing now. Such a well.
2 minutes early on Friday?
Automated.
What's that?
2 minutes early on Friday?
It works for me.
I don't know.
I guess it's.
I got another class to teach downstairs. So
Okay.
SAT solvers is search engines.
I think these are all.
All right.
I will find.
Bye, John.
I will find.
Bye. Thank you.
Thanks for calling in.
I mean,